Thanks, Tarek, and thanks everyone for coming here today. Snap started working on AR glasses about 10 years ago. And different from many other companies, we always focus on what is technically possible with a wearable standalone glasses form factor. Our first glasses were released in 2016 and enabled users to take videos and photos. They came with an easy integration with the Snapchat application to share pictures and videos with friends. Our second generation was released in 2018 and improved the capture quality and the robustness of the glasses. In 2019, we released the third generation, which had stereo cameras to take 3D pictures and videos. And then, in 2021, we released our first truly see-through AR glasses. With these, users could now experience lenses directly on spectacles, the same way they would in the Snapchat application on the phone, but now in stereo and full 3D. These were our first all-in-one AR glasses, the first of their kind with this form factor and capabilities. No tethering with a phone or an external compute unit. The displays had a 26-degree field of view, and despite the very small form factor, these glasses were able to do 6-DoF tracking, face tracking, body tracking, and some scene understanding. Nothing has come close in form factor and capabilities until today. Now, with our new spectacles, we've made another huge breakthrough in AR glasses development. These new spectacles remain untethered, enabling immersive, outdoor, on-the-go experiences. And like most great inventions, getting there required overcoming many unexpected challenges. Today, I will talk about 4 of these challenges: displays, computer vision, power consumption, and latency. Let's look at displays first. Immersive AR experiences require displays that can overlay virtual content onto the real world. Today, there are 2 main approaches that are entirely different, and they split all XR devices into 2 very distinct categories. The first category of devices uses video pass-through for its display. Essentially, it works like this. A camera captures the real world, and a computer program adds virtual content directly into the camera image. This image is then shown to the user via the display. This video pass-through usually works best when most of the view will be filled with virtual content, as it is the case with VR and MR. Because it uses mature components, such as color cameras and OLED displays, it is relatively straightforward to mass market. However, because of the large displays and the thick lenses and multiple cameras, this leads to rather heavy and bulky designs. Devices with video pass-through often look like ski goggles. Also, with this tech, there are severe limitations in focus distance, dynamic range, and image resolution. And a lot of power has to go into reproducing the real world on the screen. The second category of devices is optical see-through. This approach optically merges the real world and virtual content. The light from the real world directly reaches the user's eyes through the optical combiner, which also reflects the virtual content into the user's eyes to create an augmented experience. Optical see-through works best when only a small portion of the view is filled with virtual content, and the majority of the scene remains indeed real. One of the main advantages here is that this allows the user to perceive the real world with proper depth rather than as a pair of flat stereo images. Each real-world object has its correct focus distance. There's also no limitations in dynamic range or resolution for the real world. And it allows for compact and lightweight designs. However, there are usually limitations with display brightness, especially for outdoor use. And the augmentable field of view is more limited than with video pass-through. Today, most high-end AR headsets use waveguides. Waveguides are thin pieces of glass that guide the light of an image from one location to another. They use optical elements at nanoscale that split the light and send it into different directions, with some of the light directed to the eye and some of it directed in the waveguide to allow it to continue propagating through the glass. in-ear headsets with waveguides, there's a tiny image projector, just a few centimeters in size. The projector injects the light into the waveguide, either on the side or above the user's eye. The light then bounces inside the waveguide until it leaves in front of the user's eye so that the user can see what was the image that was emitted by the projector. As mentioned before, the light from the real world just passes through the waveguide, so real and virtual are combined optically. Because of the small projector and the thin waveguide, this approach allows for very compact and lightweight designs. On the downside, most waveguides have challenges with color uniformity, and achieving a large field of view is difficult. Also, low optical efficiency can result in high power consumption. At Snap, we use a proprietary display that was fully developed in-house and is specifically designed for our spectacles. It consists of a custom waveguide, a custom projector, and inside that projector is a custom LCOS display panel. As with cameras and OLED displays, waveguides and projectors can be acquired from third-party vendors. So why did we decide to make our own? Well, firstly, with ear glasses as compact as ours, the shape of the display largely defines the shape of the overall glasses. So if you use somebody else's display design, you have to design your glasses around that display. Instead, we start with the design of our spectacles and then design the display to fit inside these glasses. Also, having full control over all parameters allows for a more balanced design. We designed our display to optimize form factor, immersion, power consumption, and overall visual quality. And this enabled us to create the smallest and lowest power projector with outdoor usability. And the pixels inside our LCOS are, as far as we are aware, the smallest pixels in any LCOS display panel. The waveguides in spectacles use a single-step 2D pupil expansion mechanism. That's a complex word, but I will explain what it means in more detail. But most importantly, it means, different to many other ear glasses, we don't have to compromise the shape of the see-through stack due to waveguide constraints. Let's talk about pupil expansion. When the image is projected into the waveguide by the projector, that pupil is tiny, just a few millimeters in size. So if you don't do the pupil expansion, then it would only be visible in an equally small area where it exits the waveguide. I think everyone has experienced this with binoculars, where you can see only something if your eyes are placed exactly at the right location. Since spectacles need to fit many users with different interpupillary distances, and with the user's eyes moving during use, we have to expand this area to become much larger. In the image here, you see a 1D plus 1D pupil expansion mechanism, as it is used by many other ear glasses. In the top left in blue, you see the input as it comes from the projector. And because the projector is tiny, this input is also tiny. With 1D expansion, the pupil is first expanded in one direction in this green area, and then light takes a turn and is expanded again in the direction toward the exit area marked in red. You will notice that while the red area is much larger than the blue area, it is still small compared to the whole lens. In the example here, which is based on some real AR glasses, the exit area covers only about 15% of the whole lens. With our spectacles, the waveguides do this expansion in a single step. Our waveguides directly expand the pupil to its full size inside the exit area. And this enables us to make much better use of the available lens area. And as a result, the exit area of our glasses covers around 35% of the whole lens. If we wanted to make a waveguide with 1D plus 1D expansion that had the same field of view and the same eye box size as ours, it would look like this. The two 1D expansion areas would have to be pretty large. In fact, this would be a very large waveguide, too large to fit into ear glasses like our spectacles, as this side-by-side comparison shows. Okay, enough about displays. Let's look at the next challenge, computer vision. In the early days of AR, we usually used dedicated tracking hardware, such as magnetic, mechanical, acoustic, or optical systems. Those were dedicated large devices, and usually quite expensive. 25 years ago, this changed dramatically with the release of AR Toolkit, which was the first open source AR tracking library. With AR Toolkit, suddenly everyone with a computer and webcam could develop simple AR applications. All you had to do was to print out those black and white markers and hold them in front of the camera to get real-time 6-degree of freedom tracking, also called 6-DoF tracking. This means you will see virtual content in the right location and rotate it correctly. In today's AR systems, you rarely ever see those black and white markers anymore. Instead, modern methods use so-called natural feature tracking approaches. Natural features are structures in the natural environment, such as shapes or textures on objects. 6-DoF tracking is the basis of any AR system, and today we usually combine camera data and inertial measurement data into a more efficient and more robust system by fusing those two together. This works very well because they are complementary in nature. Camera data allows for accurate and absolute tracking, but it's expensive to process. And camera update rates are usually rather low, like 30 or 60 hertz. IMU data is much less accurate, but it is highly robust, and it comes at rates like 1,000 hertz, and it is relatively cheap to process. So if you combine the two in a smart way, you get a system that is accurate and robust and has a low computational cost. Let's look at the specific computer vision challenges for AR glasses, which are quite different from AR on mobile phones or AR headsets. First, because of the small size of the AR glasses, we are severely restricted in what type of cameras we can select, as well as where we can place them. These cameras need to be tiny and should not pop out, which rules out cameras with a very wide field of view. Also, because of the limited space, there are only a few places where we can put these cameras. We are also quite limited by the amount of compute power that glasses have, but we'll look at that in a later section. Also, unlike head-mounted displays, AR glasses are not rigid. Just like prescription glasses, AR glasses need to be flexible to be comfortable to wear. So they bend and twist slightly as people walk around or touch them. Also, different head sizes have quite a significant impact. Unlike traditional computer vision systems that assume rigidity, we need to constantly estimate this twisting and bending at runtime. We consider two core computer vision features for spectacles. One is 6-DoF tracking. Spectacles are much more spatial than most VR and MR video pass-through headsets, which people usually use indoors while sitting or standing. With spectacles, we expect people to walk around outside in their homes or wherever they want. So we developed a robust and highly optimized 6-DoF tracker that continuously estimates the motion of spectacles at a rate of 800 hertz. And it uses only 80 milliwatts to do so. 80 milliwatts is a very low number. For comparison, that's how much your phone uses when it's in your pocket, seemingly off. And it can work with one camera or two cameras, which is useful if, say, the user's hair covers one of the cameras. And it works well indoors and outdoors. Another core computer vision feature is hand tracking, which is our main input modality. So it's also running almost all the time. It processes images from the two color cameras, as well as the two infrared cameras. It is machine learning based and also developed fully in-house. It has an absolute tracking accuracy of about 10 to 15 millimeters and a jitter of about 2 millimeters only. As with the 6-DoF tracker, it is optimized for low power consumption and uses about 200 milliwatts only. And of course, as with our 6-DoF tracker, it works well indoors and outdoors. In addition to those core computer vision features, which basically run all the time, Spectacles also offers other computer vision features which only run when a lens requires them. One of them is scene understanding, which can generate depth maps in real time, which can then be used to do real-time raycasting. As a creator, you get the 3D location of an object or surface in the environment. This video shows a lens that uses this feature to enable the user to paint flowers onto any surface. You can also get an environment mesh when using, for example, physics effects. And of course, like all spectacles technology, it works well indoors as well as outdoors. We also include SnapML on spectacles, which enable lens developers to deploy their own machine learning networks for the lens. This is a very powerful mechanism. Look at this piano tutor lens that automatically detects and tracks a piano for the user to play on it. And by the way, it also uses SnapML to perform audio pitch detection via the microphones. So the system can check if the user is playing the song correctly. Okay, now let's look at power consumption of AR devices. Early PC-based setups, like the ones I mentioned before with AR Toolkit, typically used over 100 watts. At the time, that wasn't a problem, because they were not mobile and drew power from a wall plug. Mobile phones, which can also do AR today, have to run on their integrated battery. They can usually consume up to 5 to 10 watts. For AR applications, that means if you use too many AR features at the same time, your phone can quickly overheat. VR and MR headsets are much larger than phones and have more powerful cooling systems. They typically use 10 to 20 watts. AR glasses, like our spectacles, are highly constrained in power consumption and can only use up to around 5 watts. Let's look at why. AR glasses are wearable devices with permanent, tight skin contact. This means that the allowed touch temperature is much lower than for mobile phones. Also, they are very close to your eyes, so you really don't want them to get too hot. So what about cooling? Well, fans and heat pumps are loud. They require additional space, and they need quite some power on their own. For example, if I want to actively dissipate 3 watts of heat, I will need to add around another watt just to do that. So active cooling is not really an option for us. That means we are basically left with passive cooling, which relies on the temperature difference between the device and the environment. The amount of heat we can wick away mostly depends on the amount of surface area. The more surface area, the more heat we can dissipate. So power consumption of AR glasses is mostly limited by heat dissipation capacity. And due to the small form factor, only a little heat can be dissipated. In practice, if you have a processor somewhere here in the temple of your pair of AR glasses, that processor can consume something like 1 to 2 watts only. With spectacles, we address these power challenges through a unique, symmetric electronic design that perfectly fits the shape of glasses. Instead of one processor, as it is the case with mobile phones, we have 2 processors, one on each side. Each processor can draw up to 1.8 watts without overheating. With 2 processors, we can almost double our compute capacity. Spectacles also have 2 batteries, one on each side, and 2 vapor chambers to minimize hotspots and maximize the convectible surface area on each side. Of course, this requires a fairly complex electronic design. We have interconnects going from one side to the other that transport hundreds of signals for dozens of buses. And these interconnects also go across the hinges because the processors are located behind them. It is very challenging to create an electric connections that go across hinges. However, the processors are not the only element to generate heat. The displays do so as well. So we went one step further and separated them into distinct zones. The heat from the processors is transported backwards toward the batteries, which can also act as heat sinks. And the heat from the displays is transported forward to the front frame. To support our dual processor architecture, we developed a new operating system called SnapOS. With SnapOS, one processor drives the camera path, including all the cameras, the image signal processor, and the computer vision algorithms. The other processor drives the display path, including all the lenses, all the 3D rendering, and the late-stage reprojection for latency reduction. We carefully decided which algorithms to run where to optimize the load balance. And additionally, we included a power sandbox that controls how much power a lens is allowed to consume. We also designed our software and hardware architecture such that it minimizes the amount of data that needs to go from one side to the other, because sending data across a bus also uses a lot of power. Finally, let's look at the challenge of latency. Latency shows up as a lack of alignment between real and virtual and is usually measured in time, such as milliseconds. For example, if I move my hand and I'm holding a virtual object in that hand, then because of latency, the virtual object will always follow behind my real hand. Latency is a very challenging problem in optical see-through AR glasses. Video pass-through is more forgiving, but in optical see-through, even just 5 milliseconds can be very visible. So ideally, we would have a latency of 0, but an actual latency of 0 is technically impossible. So instead, our strategy is to get the true system latency down as much as possible and then use prediction to lower it further. So now let's look at how we handle latency and how we reduce latency on spectacles for the case of scene rendering. This is the so-called motion to photon latency, and essentially the hot path from the IMU to the display. It is a great example of how various pieces of our system work together. In our example here, on the bottom left in this diagram is the 6th tracking system, which processes camera images, which come at 30 Hertz, and IMU data, which comes at 800 Hertz. The 6th tracker calculates what we call poses. Poses describe the motion of the glasses in the environment, and the output is 800 Hertz. These poses are consumed by various computer vision algorithms, but we also send them over to the other processor on the right side of spectacles. Okay, so these 800 Hertz pose updates then go into the pose predictor, which can extrapolate these measurements to make predictions of the glass's motion into the near future. The first client that uses these predictions is the renderer. The renderer's job is to create the image that will later be shown on the display. However, it doesn't need to create the image for the glass's current pose, but for the pose that the glasses will have when the image will be visible later on the display. So let's assume it takes around 30 milliseconds from the time the renderer starts rendering until it will finally be visible on the display. So the renderer asks the pose predictor for a pose 30 milliseconds into the future, and then uses that pose to render the scene. For power reasons, it usually renders at 60 Hertz, but our display runs at 120 Hertz. We use the late-stage reprojector to make final adjustments to the frames before they go to the display. So it takes these frames, which come at 60 Hertz, and upsamples them to 120 Hertz. However, our display is a color sequential display, which means it shows red, green, and blue, not at the same time, but one after the other. So per color, it actually runs at 360 Hertz. To do this upsampling and to reduce latency once more, the late-stage reprojector also uses poses from the pose predictor, one separate pose for each color, since each color will be visible at a different time. Of course, these predictions are based on newer IMU data than what the renderer used earlier, so they have also lower latency. The output of the late-stage reprojector is not one full color image, but 3 separate images, one per color, called color planes. Each color plane only uses about 1/3 of the data compared to the full color image. So sending a color plane to the display also uses only about 1/3 of the time. Since the display will show red first, it saves quite some latency to first send just the red color plane, which can immediately be shown on the display, and then we send green and finally blue. If we had a pure camera-to-display path with no latency reduction, then the end-to-end latency would be around 80 to 100 milliseconds, which would look horrible, because as said, even just 5 milliseconds can be very visible. But thanks to this special pipeline, it is possible to reduce the true latency down to 13 milliseconds, And thanks to 360 Hz post-prediction, we can show render output on a display that has virtually zero latency, which means you don't notice the latency. Let's quickly recap all that Spectacles has to offer. Spectacles are an unparalleled device. There's literally nothing like it. It is untethered for maximum mobility. It has foldable, flexible temples for high wearing comfort. It has optical see-through displays for indoor and outdoor use with a switchable dimmer. Its displays have 46-degree field of view. And with its 4 cameras, we can do high-quality lens capture and robust computer vision. And it has 2 processors with 2 vapor chambers for maximum compute power. And all that in this small device. And we developed SnapOS for the new Spectacles. It has dual processor support for optimal load balance. It uses Snapchat's proven render engine, now also optimized for AR glasses. It does late-stage reprojection at 360 Hz, achieving a motion-to-photon latency of just 13 milliseconds. It comes with all the computer vision capabilities required for strong AR experiences. It comes with My AI as your personal assistant on the go. And it has spectator mode, so you can see lenses in real time from a third-person view on your mobile phone. We've worked hard on our new Spectacles, and it was a great pleasure seeing it all come together. Spectacles are the most powerful standalone AR glasses product ever made. And we cannot wait to see what you will be doing with them. Thank you all for being here.